Welcome to our demo benchmarking real-time image processing for offloading at the edge. This demo focuses on a robotic search and rescue scenario for industrial Internet of Things. In this use case, a robot looks for subjects of interest, like humans, in a designated area. The robot performs the task by periodically capturing high-resolution images of the landscape and running inference, that is, applying a machine learning model to identify a list of predicted objects, their location, and the confidence of the prediction. In a search and rescue mission, missing subjects may be in a life-threatening condition. The inference must be as fast and as accurate as possible. Due to computing power improvements in IoT devices, robots can now run computationally light machine learning models in real time with low battery usage. However, these models lack the required accuracy to find subjects that can be only a few pixels wide. Computationally heavy machine learning models are more accurate. However, executing them in the robot results in a significant increase in inference time and battery usage. The robot may choose to offload the inference to a more powerful local edge computing server deployed by the search and rescue team. In this work, we employed an edge server instead of a cloud infrastructure to reduce the transmission overhead. The edge server has the necessary resources to run a heavier machine learning model in real time. Before offloading, the robot encodes the image to minimize the transmission time. Featured software. For the machine learning model, we use YOLO v5, an algorithm and a family of models that aim to permit real-time object detection on a GPU. It is based on the YOLO v4 algorithm and improves its convenience. YOLO v5 offers 5 pre-trained models on the MS COCO dataset. Heavier models can offer better accuracy at the cost of more floating point operations. To encode the images, we use libjxl, the reference implementation of the JPEG XL image format specification. It generally offers a better compression ratio, image fidelity, and speed than existing image formats. JPEG XL aims to replace the original JPEG format by ensuring lossless transcoding of existing files. Experiment and results. In the search and rescue system, we wish to find a trade-off between accuracy, inference time, and resource utilization. To identify the optimal parameters for our system, we conduct 3 experiments to benchmark YOLO v5 and libjxl. In the first experiment, we study the impact of the height and the quality factor of an image on the accuracy of the YOLO v5 predictions. We selected images from the people overhead dataset that we resized and encoded in the JPEG XL format with different quality factors. The quality factor is a real number of at most 100 that controls the visual fidelity of the image. A quality factor of 100 produces a mathematically lossless image, while a quality factor of 90 produces a visually lossless image. A lower quality factor reduces the bitrate of the encoded image at the cost of a lower visual fidelity. We ran the inference on the edge server GPU and recorded the accuracy of the predictions. Images bigger than the YOLO v5 input size of 640 pixels yield more accurate results. We believe it is due to the bilinear scaling algorithm that resizes the images and favors speed over quality. Images with a quality factor of 100 generally yields the most accurate results, as long as they are at least as big as the input size. However, as shown in the next experiment, these images have a bitrate that is at least 3.4 times higher than the other quality factors, which increases the transmission time of the image. In the second experiment, we study the impact of the effort and the quality factor on the bitrate and the encoding speed to identify the parameters that allows the fastest transmission time with minimal accuracy loss. We selected images from the dataset that we cropped to 640 by 640 pixels. We selected this dataset because it offers the content diversity needed to properly benchmark an image codec. We encoded the image using libgxl with different quality factors and different efforts on the robot CPU. We ignored quality factors lower than 40 because the accuracy of the prediction is too low. Efforts are preset that enable or disable JPEG-XL encoding tools. Slower animals like kitten enable more tools to reduce the bitrate at the cost of a slower encoding speed. We ignored the effort tortoise as it is too slow for real-time processing. The behavior of JPEG-XL is not deterministic. Images with different content and resolution yield different results. However, effort generally offers diminishing returns. For example, kitten compared to cheetah allows an average bitrate saving of 10% while being 98% slower to encode. For an image of 640 by 640 pixel, this is an increase of almost 500 milliseconds in encoding time. Images with a quality factor of 100 are slower to encode than images with a quality factor below 100. We believe that this is because an image with a quality factor of 100 has more data to encode. Moreover, with a quality factor of 100, the efforts Lightning, Thunder, and Falcon offer an encoding speed that is much faster than the other efforts. We believe that this is because these three efforts disable most or all coding tools, which greatly reduces the required processing. With these results, we were able to choose what we believe are the optimal parameters for our system. In good network condition, we choose a quality factor of 100 and the efforts Thunder or Falcon. These parameters yield an average image size of 443 kilobits, an average encoding time of 26 milliseconds, and an average accuracy of 92%. In poor network condition, we choose a quality factor of 90 and the effort cheetah or faster. These parameters yield an average image size of 108 kilobits, an average encoding time of 10 milliseconds, and an average accuracy of 71%. Finally, we run a third independent experiment to understand the impact of the processing mode on the inference time. The images of the previous experiment were divided in batches of 1 to 60 images with step of 5. The upper bound of 60 corresponds to the maximum number of images that the GPU can hold in memory at the same time. For each batch, we run the inference on the edge server GPU and the robot CPU linearly, that is one image after the other, and in parallel, that is all the images at the same time. On the edge server's GPU, the total inference time is faster in parallel than linearly. On the robot CPU, it is the opposite. In larger batch sizes, a greater gap in the total inference time can be observed between the two processing modes. We believe that this is because YOLO v5 is a fully parallelized application optimized for GPU. In the linear average inference time, the edge server GPU is about 13 times faster than the robot CPU. Also, the batch sizes 1 and 5 yield different results. This is because the first image of each batch is always slower to infer. This behavior raises the average in smaller batches. The parallel average inference time increases according to the batch size. This shows an interesting trade-off for the edge server. While processing more images in parallel reduces the total inference time, the response time increases. A too high response time will force the robot to temporarily stop their search. However, if the robot chooses to run the inference locally, it should always process the images linearly. Now we will present the demo of the system. With the first two images, the bandwidth and the signal strength are high. The robot chooses to offload the images with a quality factor of 100 and an effort of thunder. The predictions of YOLO v5 are superimposed on the images. With the next two images, the bandwidth and the signal strength are low. The robot chooses to offload the images with a quality factor of 90 and an effort of cheetah.